Hey everyone. In this chapter, we're going to take a look at magnets and magnetic fields. And I know you've all, in the past, you've all experienced magnets of some sort uh, throughout your life. And you know that there's the magnetic force, okay, that we can use to attract things, sticking a magnet to a fridge. Tip of screwdrivers will have a magnet in it to hold the screws. But this chapter is going to go and explain a little bit more in depth about how that force is generated, how these fields operate, as well as look into the calculations behind studying magnetic force. But first off, what is a magnet? So the definition, if you Google it, it says a magnet is a material or an object that produces a magnetic field. Okay, and that's it's a definition, sure, but not necessarily a great one because first off, what is a magnetic field? What types of materials can produce them or objects? What is so it still doesn't really tell us what makes a magnet. So let's try to break this down a little bit. First, a couple of examples of magnets you've probably seen before. So here's a classic horseshoe magnet. Okay, we have some ceramic magnets. These are the ones that are like on your refrigerator. A bar magnet. These ones you may have seen in the lab or some other places. They're fairly strong magnets. They're called neodymium magnets. And then, of course, we have a compass with a magnetic needle in the compass. Um, so something about all of these magnets is they all have two sides. You notice some of them, like the bar magnet here. Okay, we have an S and an N, and that stands for north and south. And that represents the two poles of our magnet. We'll go into a little bit more detail in this in a minute. But we have our two magnetic poles. And every magnet will have two magnetic poles, a north and a south. This is why if you flip a magnet around, one side of it will repel certain things and the other side of it will attract. Okay, so like magnetic poles repel, and unlike magnetic poles attract. So we see here, if you put two north ends next to each other, they repel, or two south ends next to each other, they repel. Okay, opposite poles, however, will attract each other. So there's a force that pulls the two magnets in together. Materials that are strongly magnetic, we call them ferromagnets, or ferromagnetic materials. Okay, this includes iron, nickel, and cobalt as pure elements, and steel, which is an alloy of iron, okay, and other alloys containing iron, nickel, or cobalt. But these are the ones we often think of as being ferromagnetic. So essentially anything that's magnetic probably in some capacity contains one of either iron, nickel, or cobalt. Okay, and these ferromagnets, they will be attracted to magnets, okay, and be pulled in by a magnetic field, or they can be turned into permanent magnets themselves. So all magnets have two poles defined as north and south. The direction of the magnetic field is defined as the direction that the north pole of a compass needle points when placed in a point in the magnetic field. So let's put a bar magnet here again for a second. So if you remember when we studied electric fields, we had the electric field lines moving around from the positive charges to the negative charges. Okay, a magnet is very much are very similar in the way its magnetic field behaves. So you can see the magnetic field lines here on this diagram. The magnetic field lines come out of the north end of the pole, so they point away from the north and they go to the south. Okay, and the magnetic field lines will wrap around themselves on this individual magnet. So again, they go away from the north and to the south. And if there's no reason, we could have taken a magnet and we could have called it positive and negative, just like an electrical charge. We could have said north is positive and the south is negative. Okay, the names north and south are just arbitrary definitions. They didn't have to be called that, but that is how they are called, and that's how we are going to define them. Okay, so again, away from the north and to the south. So if we put compasses in the region of the magnetic field, you'll notice that the red north arrows are always pointing away from the north. So the blue south arrow here is attracted to the north. So it's going to point in this direction. And the north needle points away because it's pointing toward the south. Now over here it doesn't look like it's pointing toward the south in this compass, but this magnetic field, remember, is technically at some point wrapping and going back towards. So you can imagine it as it's going away from the north or towards the south. Now, let's think about the Earth for a second, because when we take a compass on the Earth, our needle on our compass points toward the North Pole to tell us where the north point of the Earth is. But if you think about what I just said, the north point on a compass actually points away from the North Pole. So that means on the Earth, the top of the Earth is actually the south magnetic pole, and the bottom of the Earth is actually the north magnetic pole. So a compass needle, right, is just a really small magnet. So the north magnetic pole of the Earth, like I just said, is really in the South Pole. Now the top is still the geographical north. There's actually multiple different north poles, and the south is still the geographical south. But in terms of the magnetic poles where the compass points, it is the opposite of what you would think. Okay, so a couple of different types of magnets. We have permanent magnets, which is just something with a permanent magnetic field. So those ones I showed you, like your fridge magnet, is a permanent magnet. Okay, there's magnets inside your headphones. If you've ever taken your headphones and tried to place them close to each other, you'll notice there's a little bit of repulsion in it. It's due to some small magnets in there. Okay, those are permanent magnets. You can have an induced magnet, which is a material that becomes magnetic only when it's in a magnetic field. A nail, for example, can be picked up by another magnet. The nail's not magnetic in itself, but when you expose it to a magnetic field, it becomes attracted to it. And then there's electromagnets, and we're going to take a more in-depth look at these later in this unit. But essentially, when you put a charge through a wire, you create a magnetic field. So a bar magnet is a good example of a permanent magnet. Okay, an induced magnet, you can actually try this one at home. If you take some paper clips or other small metal objects that can be attracted by magnets. Okay, if you hold a small magnet in your hand and let the first paper clip be attached to this magnet, this paper clip actually becomes a magnet in itself. And then you can use that to pick up another one, which becomes a magnet, and pick up another one. The chain will get weaker as it goes, but you can create, so this is an example, each of these paper clips would be an induced magnet. Okay, an electromagnet, if we take a coil of wire, okay, and wrap an iron core through it, so again, remember the iron itself is not necessarily magnetic, but when we put the charge through it, we turn it into a permanent magnet, okay, with the north end here, in this case, and the south end here, because it's pointing away from the north and into the south. An example of an electromagnet in real life that's used, if you've ever seen one of those junkyard cranes. So these are incredibly powerful electromagnets. They can lift up cars, but the idea is when you turn it on, so when you start the current, that creates the magnetic field, allowing the metal to be attracted, and then to drop it, you just stop the electrical current and the magnet shuts off. So electromagnets are quite widely used and very important. So why are things magnetic? To understand why something actually has magnetic properties, we have to go way down into to the atomic level and study what's going on with its actual particles. Okay, so we talk about domain theory. So on a small scale, ferromagnetic materials are made up of tiny regions known as domains, and each domain behaves like a tiny magnet with a north and a south pole. Okay, so each of these domains, we can actually kind of break it up if you want. Here's a domain, here's a domain. Okay, so you can look at it as different pieces of this metal. Now, within each of these different regions, you see an arrow. The arrow represents our magnetic pole. Okay, with the north being the head of the arrow and the south being the bottom. So currently, all of these different domains are pointing in different directions. Now, what's creating these domains is actually the electrons. So if you know a little bit of chemistry, an electron, when an electron spins, it creates a magnetic field. Okay, and depending on the direction that the electron is spinning, is it spinning clockwise or counterclockwise, will change the direction of the magnetic field. So what this domain actually represents is we have a bunch of electrons in, say, this one here, and all of these electrons are spinning in the same direction, causing a permanent magnetic field with a north and a south pole, because they're all compounding on top of each other, creating a stronger field. This region next to it, again, has a bunch of electrons, all pointing in the same direction, but they're not pointing in the same direction as this domain. Okay, so these two domains, we see the norths are almost opposite each other. So overall, in a material, the domains tend to cancel each other out. And this is an unmagnetized material. But if we can align all of these domains in the same direction, what we do is we create an overlapping effect of magnetic fields with a north end, a total north end summed up on the left here and the south on the right. So by aligning all of the electrons, or we align all these domains, which allows us to magnetize a material. You can actually try this. If you have a screwdriver, if you even have a fork, you can magnetize a metal fork or a knife. So all you need is a bar magnet. So you need to have a magnet that distinctly has, you can tell what its north end is and its south end. You take that magnet, bring it up to your object, so stick with the north end, and slide it along the object. So do this a couple of times repeatedly. Okay, and you slide it along and along and along. And what this does is the domains and the electrons in the metal object will start to all align in the same direction as they're attracted to the magnet that you're pulling along the object. So you can actually magnetize a knife or a fork and use it to pick up other metal objects. So if you have a magnet at home, you should go and try this little experiment. So again, here's an example of the knife. So in aligned domains, you can use a regular old knife, turn it into a magnet. Okay, so the domain theory helps us understand the behavior of magnets. So the poles, notice that in this image here that they're using the end of the knife to pick up the fork. Okay, they're not using the middle of it. And that's because the magnets are strongest at their poles, since this is the only location where domains do not cancel each other out. If you were to take that knife there that's magnetized and you were to drop it or you were to heat it up, it would actually scatter and mix all the domains again, so it becomes non-magnetic. This is why if you're ever using a compass and you're in the field or something, it's very important not to drop or rattle your compass because it will demagnetize it. Okay, and breaking a magnet in two, so if we were to crack that knife in half, it would actually still be magnetic. Each half would then be magnetic with their own north and south poles.